Good afternoon, everyone. Thank you for joining us today. Today's the second day of Earth, Energy, and Environment E3 Conference and Exhibition, second year 2022. My name is Romana Tariq Abdurazek. I'm a petroleum engineer, a recent master's degree in petroleum engineering graduate from University of Houston, currently working as an engineer in Houston, Texas. I have the pleasure to be here with you this afternoon as a member of the Technical Committee of Earth, Energy, and Environment E3 Conference and Exhibition. Today, we're pleased to welcome our invited speakers, one of which is Mr. Stephen Nolet. After a bachelor's and a master's in aeronautical engineering from Massachusetts Institute of Technology, MIT, Mr. Stephen Nolet worked in the oil industry and was the vice president of engineering at Fibrous-Par line pipe for over the past 10 years. Today, he will be discussing the future of wind energy. This session is being recorded and will be uploaded to our YouTube channel, PioPetro, where you can also find all of our previous and upcoming sessions in Earth, Energy, and Environment E3 Conference and Exhibition. Again, that's our YouTube channel, PioPetro. Please feel free to send your questions in the chat box, and we will answer as many questions as possible. With that, I ask you to give your full attention to our invited speaker and help me in welcoming today's very honorable guest. Please welcome Mr. Stephen Nolet. Hi, Mr. Stephen. Thank you for joining us today. We're so glad to have you on Earth, Energy, and Environment E3 Conference and Exhibition.
It's a pleasure. Thanks for having me. I want to thank everybody, the organizers of the E3 conference. It's a wonderful opportunity to address the students and our future generation. Energy independence is such an important part of our future and our global security. So it's an honor to speak to you, and I wish you very well on your careers. You're working in the right technologies at the right time. As Joanna said, I'm Steve Nolet. I'm Director of Innovation Technology at TPI Composites. We're a manufacturer of large utility scale wind turbine blades. And I'm going to talk about wind energy today and the future of wind energy. But what I want to convince you of is that the future is now. We're deploying reliable, technically capable energy systems that are impacting both the national and international ability to build a sustainable energy future. What I'd like to talk about today, I'm going to cover a lot of ground, so I'm going to cover it quickly and try to stay on track. I don't have nearly as much time as I could spend with you talking about wind energy. We'll talk a little bit about energy and power as it relates to wind. I'll give you an update on the global growth and the facts about wind energy. Talk a little bit about the technology of wind and describe horizontal and vertical axis wind turbines and why we have settled where we have in utility scale wind. We'll talk about the meat of our discussion, the techno-economics of wind energy, particularly the power that's in the wind, which is our foundation, the language of wind, and how we describe the performance of wind energy. We'll look at the power curve, wind resources, and talk about the cost of energy generated by wind, and talk a little bit about the trends in wind energy today and our place in wind energy. All right, and then we'll wrap that up and finish our day. Let's talk just a bit about energy. You guys are all experts in the field, so I don't need to tell you what energy is. It's difficult to conceptualize. You can't hold it in your hand. But when we talk about energy, we can quantify it. And we talk about kinetic energy. And kinetic energy is important to us in the wind and industry because that is what we're converting to different forms of power or energy. And so we all know the equation for kinetic energy, right? 1/2 mv squared, where m is the mass of an object in motion, the v is its velocity, and the resulting units, kilogram meters squared per second squared, are joules, right? We all know this. We also know that potential energy in the same units is the mass times its gravitational attraction and its distance of potential travel, mgh. Other units that we might talk about besides joules, calories, British thermal units, ergs, foot-pounds, newton meters, and even that thing we see on our power energy bill monthly, the watt hours, is a description of the energy, the quantity of energy that is consumed or used or transferred. There are many other ways to describe energy, but at the end of the day, it's the capacity to do work. And we use and harness energy to do work. Remember, energy and power, they're closely related, but not the same thing. Energy is the ability to cause change, but power is the rate at which energy is transferred, right? Again, fundamental, we know that. We talk about power is the change in energy, change in the energy of a system divided by the time that change occurs. And we divide a joule per second, we call that a watt. Take 1,000 watts and we call it a kilowatt. Then multiplying the power over a period of time is the energy that is being used, right? And I would just mention there's 3.6 million joules in a kilowatt hour of energy. All right, let's shift gears, talk more about wind now. It turns out 2020, despite the pandemic, was a pretty good year for wind energy, particularly in the US, in which 16 gigawatts of increased capacity was added to our electrical grid. And similar performance in Europe, where the installed capacity across Europe reached 220 gigawatts of installed capacity. Much of this is due because of the changing and growth in the technology, where the average power rating of machines tendered in 2020 rose to 4.2 megawatts per turbine, as a result of turbine technologies that are now exceeding 5 megawatts per turbine. These are very large machines. Also in 2020, at the end of the year, the Biden administration, actually during 2021, the Biden administration announced an ambitious but achievable goal in North America of installing 30 gigawatts of offshore wind in 2030. The Europeans have been working on and installing large capacity of offshore wind in the North Sea for about a decade now, and we have a long way to catch up in North America, but that growth is already beginning. Dominion Energy commissioned a 12 megawatt project in 2021, and New York State has committed large resources to building both an infrastructure and a capacity with leases issued in the Long Island Sound. And so offshore wind is coming to North America very quickly. Well, the nation's energy capacity, the United States energy electrical generation capacity grew a lot, as I said, by 16 gigawatts in 2020. And now in the fall of 2022, we have an installed capacity of 140 gigawatts. But there are technical challenges that remain. As you see, a large sector of the country, particularly the Southeast, has a very low, next to zero installed capacity. And that's not a political statement. That's a fact of reality of the lack of resource at ground level to generate power from the wind. With taller towers and with larger capacity factors, it's going to turn out that above 80 meters, we can build out capacity in the Southwest and across the country with a potential capacity of up to 10 terawatts of electrical energy generating capacity. The challenge is a technical one, and we can meet that technical challenge with new ideas and new approaches to building our wind turbines and the generators that create the electricity that we need on a daily basis, particularly as the electrification of our economy continues to build out in transportation sectors and in other needs. Fundamentally, there are two types of wind turbines that we build and deploy. The most common that you'd be familiar with are what we call the horizontal axis wind turbine. So the name is self-evident. The axis of rotation is horizontal to the ground. So we call these HOTS, horizontal axis wind turbines, and they come in all kinds of flavors, but you're certainly most familiar with the three-bladed upwind HOT that builds out our utility scale generating capability. But there have been other technologies developed and demonstrated, including ducted turbines, to increase the swept area, the effective swept area of the wind turbine and capture more energy. Less familiar, but you probably recognize, are the vertical axis wind turbines, such as this Darius generator that was built in the 1970s to more architecturally aesthetic Darius vertical axis wind turbine generators. And offshore systems that have been conceptualized, designed, and still remain on the drawing board are possible as well. There are other types of horizontal axis generators called Savonius machines that use drag to drive or create torque that will turn a generator and create electrical power. But the jury's in. The horizontal axis wind turbine is the de facto winner of the utility scale wind turbine race. While a hot needs a way to keep the rotor facing into the wind in order to create lift on the blades, and that lift is then turned into torque, and the torque turns a drive shaft, which turns a low-speed shaft that then rotates a gearbox to turn a high-speed shaft and run a generator. On large turbines, that a drive motor is used. So we have a control system that is driving the nacelle and pointing it ever into the face of the wind. With the Vats, they're much simpler. The Vats operate without yaw bearings and are always pointed into the wind regardless of the wind direction. Both the Hots and the Vats create torque to turn a generator through airflow over wing-shaped blades. Specifically the Darius Vats, not the Savonius, which are drag machines. Horizontal axis blades, though, they generate lift throughout their full 360 degree of rotation, right? And with vertical axis machines, they lose lift as they turn away from the wind, and they actually create drag on the system. That drag is designed to be quite low, but they simply do not generate power through the interaction with the wind through the full 360 degrees of rotation. They're simply less efficient in converting kinetic energy in wind to torque to drive a generator. And since we understand wind shear, where wind velocity increases with elevations, Hots have a natural advantage of being situated at a higher elevation and therefore subject themselves to more interaction with higher velocity wind. And that'll be an important consideration when we talk about that in just a moment. Now, Vats, with their smaller tower and their ground-mounted generators, that makes them less expensive to deploy, to erect, and less expensive to maintain. Although reliability remains a problem because of the overturning moment on their bearing. So while they may be easier to maintain, they have higher operation and maintenance costs. We'll talk about why that's very important shortly. Utility scale Vats inevitably require, when we say utility scale, we're talking very large systems, require some form of guy wire at the top of the tower to stabilize it and overcome some of that moment. And it adds to the footprint of the machine and affects the airflow. Now, it turns out that Hots have really won the technology battle at the utility scale. And we'll see why as we talk about cost of energy in just a bit. We look under the hood of a horizontal axis wind turbine. They're really sophisticated and glorious machines. Sort of a mechanical engineer's dream, if you want to know the truth. Of course, we understand the blades, and I'll talk more about blades in a bit, but those blades are connected to a hub, and the hub is connected to a low-speed input shaft that is generally part of the system, where a gearbox then increases the speed of the rotation to a high-speed shaft through gearing. And through that high-speed shaft, we turn a doubly fed induction generator that will create the electrical power that is fed to the grid. And unique and wonderful power electronics that keeps that signal synchronous with our electrical grid to feed that power seamlessly to users and the consumers. Always a meteorological tower on the turbine to provide control inputs, direction of the wind speed, which will then turn or send commands to pitch motors that turn a pitch bearing that rotate the blades to either increase the lift through increasing angle of attack, or feather the blades away from the wind when the wind is overpowering the turbine, much like a sailor would let out the sheet or pull in the sheet to change his angle of attack on the sail. We do the same thing with the wind turbine as well. I mentioned the yaw motor at the bottom of the nacelle connected to the tower. That's commanded by the commanded by the weather vane that tells which direction to point the blades towards to face the wind. A wonderful machine, wonderful, and these are common. These elements are common to all machines. There are larger machines today that are using direct drive systems, where the shaft from the rotor is directly fed to the generator. This requires very large rare earth magnets on very large running generators to create the velocity to create asynchronous electrical power for the grid. All right, let's talk a little bit about the energy that is in the wind, right? If we're gonna create electrical power, we have to convert that kinetic energy in the wind to torque, and from torque we can turn a shaft and we can turn a generator. What is the power in the wind? We talked about kinetic energy, and the reason I talked about kinetic energy, because that is what we're harvesting, that kinetic energy in the wind. And we can describe that as 1/2 rho pi r squared v cubed. That doesn't quite look like 1/2 mv squared, does it? Well, that's because we're going to take into consideration the density of the air, the constant pi multiplied by r, which is effectively the length of the blade. So pi r squared is the swept area, with the density of the air as rho, and the velocity of the wind that passes across the rotor. Pi r squared rho v is the mass that passes across the rotor and interacts with the blades. So this reduces to our kinetic energy equation, where the swept area is pi r squared, of course. And if we were to look at units where we have kilograms per cubic meter, the mass of the air, and we have meters squared, the area, and meter cubed per second cubed is the wind velocity, the mass of that air across per second cubed, that we have our units of watts power generated. So that's the power in the wind, 1/2 rho r squared v cubed per second, joules per second. So our kinetic energy multiplied or integrated with the time is our energy, and our power in joules per second or watts. So if we look at this equation, then the power scales linearly with the air density, right? So in the summer, where the air is a little less dense and in warmer air, we produce less power. In the winter, when the air is denser, we can produce a little bit more power. This is a couple percentage points difference in the density of the air, but that's not where we create our power. The power goes up at the square of the blade length. So if we double the length of the blade, we have 4 times more power output, given all else being the same. But much more importantly, of course, is the power in the wind. It's increasing with the cube of the velocity of the wind. So it's low wind, so very low wind, not much power, but we go up with the cube. We increase our power output with the cube of the wind velocity. And that's rather compelling and will drive our choices for siting of a wind turbine. Right? What about efficiency? How do we describe the efficiency of a wind turbine? Do we convert all of the energy, all of that kinetic energy in the wind to electric power? The answer, of course, is no. In order to be able to do that and to harvest 100% of the kinetic energy of the wind, we'd have to convert all of the movement of the air molecules to torque to drive the shaft to create our electric power. That means that after the air passes through the turbine rotor, it comes to a stop. In other words, the velocity is equal to 0 meters per second. Now we've got our cartoon wind turbine. We've got air molecules wanting to rush through. That can't possibly happen. We can't stop the wind behind it because we'll create a traffic jam. And if the air doesn't move behind the turbine, that means it comes to a stop and no more air can flow through our turbine. So it's simply not possible to convert all of the kinetic energy to electrical power. But what's that limit? We call that limit the amount that is conceptually possible, the maximum energy possible to convert. We call that the Betz limit, right? The Betz limit from Albert Betz in 1919. So we've known about this for a long time. We solved the problem in a longer course. I could teach and derive the Betz limit. It's quite straightforward. But what is that Betz limit? We'll talk about it in just a minute. But before we do that, let's talk a little bit about energy production terms when it comes to wind energy. The power in the wind, as we said, is 1/2 rho pi r squared v cubed. And we talk about something that we call the rotor power coefficient. The rotor power coefficient is how effectively we interact with the wind and harvest that percentage of power that's available. And we'll look at an example of that right now. The CP is defined as the fraction of power in the wind that's converted to mechanical energy. In other words, P equals CP times 1/2 rho pi r squared v cubed. Simply a coefficient describing what percentage of the power in the wind we convert to electrical energy. The Betz limit says that the maximum coefficient of power that is possible, that is theoretically possible, is 59.3%. I get calls almost on a monthly basis from people across the globe that have a better wind machine. And the first thing we'll look at to determine whether or not they're selling me a perpetual energy machine is to look at their CP of their system. If it exceeds 59.3%, they're selling snake oil. That's a theoretical limit. But we'll talk about rated power, though. The rated power of a turbine is the maximum power that the generator can produce. And we'll look at that a little more closely when we look at the power curve. Probably the most important factor of a wind generator, when we talk about the economics, is the capacity factor. The capacity factor is the average output. It's defined as the actual energy generated divided by the rated energy measured over some specific period of time, typically over a year. So if I have a 2.5 megawatt wind turbine, and over the course of a year, its average output is 1.25 megawatts, then its capacity factor is 50%. We'll look at that in more detail shortly, but I think it will make more sense briefly. The cut-in wind speed, that's the wind speed where energy production begins. Typically, that's about 3 to 5 meters per second. Below that, there's not enough wind, there's not enough kinetic energy in the wind to even bother with. There's not enough energy to even start the rotor to turn and sustain power generation. Note that a meter per second in US terms anyway is about 2.237 meters per second, or about 3.5 kilometers per hour. We talk in wind energy because of consistent units. We always talk in meters per second. The cutout wind speed is the wind speed where energy production ends. And that's about 25 to 30 meters per second. If you convert that 30 meters per second to miles per hour, that's a very strong, that's in the class of a hurricane. We continue to produce energy up into the power of a hurricane. And you might ask me, Steve, why don't we keep the generator running? Well, we'll talk about that in a moment too, but I think you can imagine at some point a turbine can become overpowered. And when it becomes overpowered and the blades deflect far enough and they strike the tower, that's a bad day in the life of a wind turbine. Let's talk a little bit about turbine efficiency and the power coefficient CP. We defined the CP as the energy produced by the wind turbine divided by the total energy available on the wind at any given wind speed. We can write that then, right, as CP is 1/2 rho, the swept area of the blade times V cubed. And if we say, for example, that a wind turbine converts 70% of the Betz limit into electricity at a rated wind speed, then the CP is simply that 70% of 0.593 which equals about 0.4. So the wind turbine converts 41% of available wind energy into electricity. In fact, that's pretty good value. Typical power CPs of modern turbines today run in about 35 to 45% range. Right? 35% to 45% of that kinetic energy directly converted to electrical power supplied to the grid. Let's look at this in a little more detail. Let's think about a 48.7 meter wind turbine blade. When I wrote this slide up a couple of years back, that was sort of a nominal size of a wind turbine, a 2.5 megawatt or maybe a 1.7 megawatt machine with a rotor CP of 39%. If we look at the power output in the wind or the power output of a turbine on the y-axis versus the wind speed in meters per second, the blue line represents the total power in the wind. That's our power in the wind equation plotted in terms of kilowatts as a function of the wind speed. The Betz limit, which defines the maximum that's available for us to turn into electrical energy, is the red line, and then multiplied our CP rotor at 39% CP is the green line. All right, so that tells us that at 30 meters per second, our turbine is capable of producing 50 megawatts of power at 30 meters per second. That's a lot of power. And yet I'm telling you that this turbine is rated at about 1.7 to 2.5 megawatts. Why is that? Well, we'll look at that in just a minute. Let's look at it a little bit more closely. Let's look at the capacity factor. Capacity factor is the fraction of time, usually over an annual period, that a turbine is operating at its rated peak power. The capacity factor is the average output divided by its peak output. Capacity factors are typically 30 to 50%. In fact, modern wind turbines today that we're putting in the field all have capacity factors on the order of 50%. The capacity factor is a characteristic of both the turbine, what we rate the power at, and the CP, the power coefficient, but it's also a function of the site characteristic, right? How much wind is blowing? How often is the wind blowing? How much continuously? Do you have long periods of low wind speed where you're not producing much power? So the capacity factor is a combination of turbine technology and siting, meteorology, where we put a turbine. In theory, the capacity factor can be 100%. We could, if sited on top of a mountain, on top of Mount Everest, possibly, or some location that's ideal, operate the turbine continuously at its rated power. Maybe offshore. Capacity factors offshore will always be higher than onshore installations for a number of reasons. But for one, I think, as we all know, offshore, the wind is blowing more continuously. Turbulence factors are lower. Wind shear is less of a factor because it's flat and continuous. So our capacity factors, our performance of the wind turbines are better offshore. Now, let's get to the point about capacity factor, rated turbines, and look at the power curve of a modern wind turbine today. Here's our plots again. Power in the wind, blue line, Betz limit, red line, the CP power of the turbine, the green line. And let's talk about a 1.7 megawatt rated machine, for instance. All right. What's that mean if a turbine is rated at 1.7 megawatts of power output? That means it's low speed shaft. It means it's gearbox. It means the generator, all of the power electronics, the wires themselves, the physical cables that carry current, the tower, the foundation, the grid connection, everything that makes up that turbine are all sized to handle no more than 1.7 megawatts of power. Why wouldn't we increase that? Well, it would cost a lot. It would cost more money to increase it for that turbine. And so we build what we call the power curve, which describes the powers that turbines output as a function of the wind speed in terms of its rated power. Again, let's look at what on the x-axis, particularly from 0 to to about 3 meters per second, we don't even create any power at all. That's lower than the cut-in wind speed. And then we have the cut-out wind speed at about 27 to 30 meters per second, where the wind is so strong that we can't feather the blades and we can't generate more power. We risk damaging the components of the wind turbine, so we cut out and stop producing power. Remember, that's a hurricane, right? We don't live in places where hurricanes are blowing continuously. In fact, the turbine spends most of its time working in region 2 of the power curve, somewhere between maximum rated power and the cut-in wind speed. And in this region is where we're applying technology to maximize the output of the turbine. Once we hit, say, 10 to 12 meters per second, the rated wind speed of the tower where it produces the rated power, then above that wind speed, we begin to feather the blades to prevent overloading the turbine. And these are very windy days. Anything above 15 meters, that's 35, 40 miles per hour. We don't live in places and on the planet where the wind blows, but there are times where the wind is blowing at that power. We want to generate power, and we feather the blades to reduce the load on the blades, load on the machine, load on the tower, and all of the components to prevent damage. And we have what we call the power curve of the wind turbine. All right. Let's talk about the wind resource itself. The wind speed at any given location is continuously varying, right? This variance can be observed in changes in the annual or seasonal or with weather systems or on a daily basis, different times of the day, and from second to second, which we call turbulence. The turbine choice and the rotor design depends on the probability of extreme winds. It may be more significant, that may be more significant turbulence as a result. And that impacts the fatigue life. And turbulence and high extreme winds affect the fatigue life of the blades and the gearbox on the generator and our foundations. Turbulence is quantified with a metric that we call the turbulence intensity. And it's the statistical variation of the horizontal wind speed as a function of time. And we measure that over some period of time. We average it and we create the turbine intensity factor, which will impact how we design that blade, what rotor we size it with, and how robust the mechanics of the system must become. Globally, we use wind resource maps as an important tool for siting wind turbines. In the United States, of course, a lot of us already know that wind energy is centered in much of the Midwest and Southwest Texas. In fact, Texas leads the country in terms of total installed wind capacity in America. And in Europe, which has a large amount of wind power, it's dominated along the southern part of France, in eastern Spain, in northern Germany, and in the Baltic coast, and in the North Sea off of Great Britain. Tremendous wind resources in Denmark and the Scandinavian countries as well. We use those wind resource maps to help us start the evaluation of location of wind. Notice off the coastal United States on the East Coast, tremendous wind resources there as well. And we could say the same about the North Sea and in between Great Britain and Ireland, tremendous resources of wind, offshore wind as well. Well, to help organize this, the International Electrotechnical Commission established a set of wind classes. Lower the wind class, the higher the average wind speed. So we have class 1, class 2, class 3, and class 4. And depending on the wind class, we can talk about the power density, the nominal power density in the wind, from 600 watts per square meter down to a measly 130 watts per square meter in class 4 wind sites. We are beginning to develop class 4 wind sites as the number of more resource-rich sites have been developed. And that requires technology and technical development that I'll talk about in just a moment. When we think about that wind resource, it's seldom uniform. As I mentioned, we worry about the wind turbulence, the wind shear. It's different at ground level than it is at the tip of the blade at the top of its rotation. We have influence from upwind turbines. Most turbines are located as part of a wind plant or wind farm. And so upwind turbines can influence downstream turbines based upon their siting and the direction of the wind. Terrain features and structures will impact the incoming resource, all of which will affect the dynamics of the wind turbine. It impacts our energy production. It impacts the life of the blades and life of the drivetrain and the O&M costs, the operational and maintenance costs also. And now let's go offshore and think about floating machines, the dynamics of the movement of that foundation with relationship to all of the other components. Tremendous dynamic problem to solve, and the challenges of structural engineering, ocean engineering, tethering it, the offshore oil and gas industry have been a tremendous boon to offshore wind in developing an infrastructure and the capability to erect these and station these massive structures. Talked about wind turbine efficiency a lot. But the real question I would have is, what does that mean? It's kind of like saying, I mean, the wind is free. It blows constantly around the globe. If the input isn't completely utilized, it's not like we've lost anything other than opportunity potentially. But let's face it, the overwhelming volume of wind, kinetic energy, goes untapped. We don't see any mortal consequences. Now, I think that the real metric to discuss when we talk about wind energy or almost any energy system is the cost that it requires to produce that energy. The logical metric to discuss is the cost of energy produced by a wind turbine and compared to maybe other sources of energy, such as a diesel turbine. I chose this particularly because this is the site of the first U.S. offshore wind plant off of Block Island in Rhode Island in the United States. They replaced all of their energy that was being generated by diesel turbines on the island with the energy produced by the six massive 5+ megawatt machines that are stationed offshore. This is expensive energy, but compared to the diesel generation, it is a fraction of the cost. We'll talk about offshore wind in just a moment. How do we make the power choices based on the cost of power? Well, we introduced something we call the levelized cost of energy as a useful metric, and we could have lots of discussion about this, particularly as it relates to renewable energy versus carbon sources versus solar versus others. And we want to have that discussion. Levelized cost of energy allocates the cost of energy of any given system across its useful life to give an effective price per each unit of energy that energy system generates. It's like averaging all the upfront costs across production over a long period of time. Levelized cost of energy is a single metric that allows us to compare different types of energy systems. Renewable projects generally have very high upfront capital costs, and the fuel cost is near zero. Whereas a natural gas plant, where the capital cost is much lower, the fuel costs are much higher. How do we compare those systems? Well, levelized cost of energy allows us to do that. It actually can be used to compare the price you'll pay on your utility bill when we talk about dollars per kilowatt hour. Well, the calculation of LCOE, and I can hear a lot of people already probably exclaiming it, is an extremely complex calculation. It can incorporate costs and offsets and credits available from a variety of different financial instruments. And that can even vary from region to region, making that comparison challenging based on local regulation, local availability of offsets. But to level the playing field and to relate one technology versus another, we still use this. It's a useful metric that will incorporate the costs that are, and particularly as engineers, we want to consider those costs that we can control: efficient design, lightweight design, reliable design. That can all improve the levelized cost of energy for any given energy system. Well, it's pretty easy to express. Levelized cost of energy is generally accepted to be the capital cost plus what we call balance of station, O&M cost, cost of money, divided by the total energy produced by that energy system. So CapEx, of course, is the price of a wind turbine, for instance, divided by its operational years of service. So as we say, we're gonna bring that upfront cost and spread it over the lifetime of the system. Balance of station cost divided by the number of operational years of service. As turbines get older, of course, it's going to create larger maintenance challenges and more time and cost and money in O&M. So that's going to increase over the cost, but we average that over the number of years, and that's a projection. Generally, O&M costs are difficult to predict on new systems. And of course, the cost of money, the cost of financing a project, the interest rates divided again by the operational years of service. And at the bottom of the denominator, the annual energy production. The more energy we produce for the given set of fixed costs, the lower the levelized cost of energy. We can combine all that and look at there have been several different organizations. Lazard is one, but I've provided a reference if you wanted to read the full report and the assumptions behind it. This is the levelized cost of energy over the past 12 years for a variety of different energy systems. And you can see this rather large reduction in cost. That's not wind energy. That's the cost of solar energy, which has come down to about $37 per megawatt. Wind is very close at $40 per megawatt. We had our rapid decrease in cost before 2009, but when this first started, it's 100. When Lazard started taking accounting in 2009, it was at 135. So we've seen about a 70% decrease in the levelized cost of energy, where solar power has seen a tremendous 90% reduction in those costs. But I want to talk about offshore wind. Offshore wind is probably a significant component of the future for wind energy around the globe. We see these installations becoming larger and larger with 13, 15, and even now 16 megawatt machines with over 240 meter diameter rotors being erected in offshore environment. Today, the costs are simply higher. The CapEx, the offshore hardware is more expensive simply to survive a marine environment. The balance of station costs, those costs to erect and to transport the material and erect and tether to the ocean floor or drive pilings and use jackup rigs to put in those pilings to mount these offshore systems are simply more expensive. Because the risk is perceived to be higher, generally the cost of financing a project is higher. And the O&M costs for maintenance offshore require specialized training, specialized deployment vessels, and a huge effort to repair and bring an offline turbine back online. So reliability is super important in the offshore environment because the offshore costs can be so much higher. Well, my company builds wind turbine blades. That's what we do. This is a measly 48.7 meter long wind turbine blade in construction in our factory in Newton, Iowa. But the trend, they're getting bigger. Every single product cycle, we're seeing 5, 10, 15% larger increases in the length of these blades. And that goal is to reduce the levelized cost of energy. We know that energy production is increased with swept area, R squared. as a manufacturer, we're seeing blades designs that are continuously being extended for a given fixed asset. Turbines that were rated at 1.5 megawatts swinging a 34-meter blade 15 years ago, that same fundamental turbine is swinging 60-meter long blades today and have been uprated to 2.5 or even 3 megawatts. Currently, the single most important driver is increasing that capacity factor, the amount of energy relative to its rated power that it's generating on an annual basis. How big is big? Well, a few years back, the 61.2 meter blade that we were building for General Electric surpassed the wingspan of a 787 Boeing aircraft. So our current blade sizes are now 55. No, they're not. They're not even 65. Most of the blades we're building today are in the 75 to 82 meter length, and that's for onshore installations. And there are really no end in sight. Recently, GE and at their subsidiary LM Wind Power produced the 107 meter long blade for the Haliade 12 meter offshore wind platform. That was quickly trumped by Siemens Gamesa that put out 114 or 117 meter long blade, and the length wars are going on. When it comes to wind power, size does matter. All right, let's wrap this thing up. Energy is likely to be the single most important component of modern day life, probably after running water anyway. I think all of you are here because of that, and I commend your choice and career. Wind generated power is competitive, it's sustainable, and the installed capacity is constantly expanding. It's an important part of a broad energy generating portfolio that is going to necessarily include solar power and gas power and nuclear power, and hopefully one day fusion power. And I hope that one of you on this meeting today takes part in that kind of discovery. Annual energy produced is a strong function of the resource availability in wind, and its trend to taller towers to increase availability is a constant trend. The economics of wind energy demand higher capacity factors, and that's trending towards larger rotor diameters and longer blades. Offshore wind will provide an ideal opportunity for acceptable siting, both from a social perspective as well as a technical perspective. You can expect that to continue to occur. But costs are much higher, so we have a technological challenge to bring those costs down and create economically sustainable systems as well. Capital equipment, balance of station costs, O&M costs are all higher, but the opportunities for increasing the annual energy production makes that potential so important for the future of our electrical generation to power the world. Thank you for having me. Dr. Solomon, thank you very much. Ahmed, it's a pleasure. I'd be happy to take a few questions now. You guys have had a long day, I'm sure.
Thank you very much. Obviously, you're so excited about the subject. I like that.
Imagine that.
This is great. There is a lot of questions. However, we are run out of time.
Yeah.
What we are going to do, we'll ask Dr. El-Garhi will capture all these questions and will forward them to you. And students, please, audience, please send the questions, more questions to Dr. El-Garhi. I am sure you have a way to access him. Is that right, Dr. El-Garhi?
Yes, correct. You know, my email easily to be found on Marietta College website. Easily, you can ask Google about it. So, and I will copy all the questions written here, and I will send it to Mr.
Actually, mine is as easy. All you have to do is to get in UH website, Petroleum Engineering Department. I will be the first person and the rest of the faculty.
I'll be very happy to address any questions.
Very good. This was a great presentation. you have a lot of knowledge of the subject. That's really great.
Well, it's an exciting area, and anybody
Yeah.
who's working in the energy field in renewables could find a very strong career here as well.
Yeah.
Thank you very much for the opportunity.
Thank you,
It's
sir.
a pleasure to address everybody.